Hello, Sarah Miller here, and this week we'll be talking about electron domain domains and molecular geometries of molecules. The geometry of atoms, in general, the geometry of atoms bonded to the central atom of a molecule depends on the number of covalently bonded atoms and the number of lone electron pairs attached to the central atom. We'll be using balloons to visualize how the electron domains take up space and computer graphics to look at the specific molecular geometry, the number of electron domains, the type of molecule, the electron domain geometry, the number of lone pairs and the placement of the lone pairs, the angles created by the electron repulsion, and the molecular geometry within these specific examples. So let's get started. So the electron domain geometry for trigonal planar with the molecular geometry of bent with the example of sodium dioxide would have 3 electron domains. And if we switch to the next slide, we'll see that this is because it has a lone pair of electrons on the other side of the 2 oxygen atoms, and this kind of evenly distributes the electron domains, which we'll see when we pull up the balloons. And so the total number of electron domains would be 3. And as we move on to the electron domain geometry of tetrahedral, if we had the molecular geometry of trigonal pyramidal, and using the example of ammonia, we would see that there's 4 electron domains, and that's because, again, we have a lone pair, if we go to the next slide, of electrons on the central nitrogen atom. So we have 3 hydrogens and then one lone pair of electrons to kind of space out the electron domain geography. And so this will give us, again, the tetrahedral geometry as depicted by the balloons. See. And so another example of tetrahedral electron domain geometry with the different molecular geometry of trigonal pyramidal. Sorry. So not trigonal pyramidal again. So this example would be bent. And an example of bent geometry with the electron domain of tetrahedral would be water. And so the total number of electron domains here is 4, and that's because there's 2 lone pairs. If we go to the next slide, there's 2 hydrogen atoms connected to the oxygen atoms, and then 2 lone pairs attached to the oxygen atom as well, which creates 4 total electron domains on the oxygen atom, and that's what gives it the tetrahedral shape. And the angle for each of the lobes of the electron domains is about 109.5. And so if we keep going, the next electron domain geography we're going to talk about is trigonal bipyramidal. And so the molecular geometry here is seesaw shaped. So the total number of electron domains here is 5. So that's because there's 4 bonded electrons and then one lone pair. Actually, the graphic chopped off the lone pair, it's supposed to say 1. But yeah, and an example of this in real life would be sulfur tetrafluoride. So if we go to the next slide, we'll be able to see the lone pair of electrons sitting on top of the sulfur atom. And we'll also see that there's 2 different angles to think about in the the triagonal bipyramidal electron domain geometry. So there's the 90-degree angle between the straight piece and the 3 kind of more horizontal or planar pieces, and then there's a 120-degree angle between the three central pieces. We can go to the balloon example and kind of see more how there might be a wider angle between some pieces than others. So the next electron domain we're going to talk about is again trigonal bipyramidal, but this time T-shaped instead of seesaw. So the total number of electron domains is still 5. The number of lone pairs here, though, is 2, and a real-world example is bromine tetrafluoride. And yeah, if we go to the next slide, we can see that there's 2 lone pairs situated on the bromide atom. And again, we have the 2 different angles going here. And yeah, with that, we can go on to the last trigonal bipyramidal electron domain geometry, which is linear. And so this is going to have 3 lone pairs on it. And a good example of this is carbon dioxide. So carbon dioxide has 2 oxygen atoms bound to it, and then 3 and then 3 lone electron pairs. That's not right. Yeah, so I know it says carbon dioxide here. That's a mistake. It should say iodide difluoride. Iodine difluoride. Okay. So yeah, I know it says carbon dioxide, but it's actually supposed to be iodine difluoride ion. So yeah, so it has 3 lone pairs, and again the 5 electron domains. And here we see where the electrons are actually placed around the fluoride molecule, or the yeah, the iodine molecule. And last but not least, we have the octahedral geometry. So this electron domain geometry has 6 different domains available to it. And the first one we're going to look at is square pyramidal for the specific molecular geometry. The number of lone pairs here would be 1. An example would be bromine tetrafluoride or pentafluoride. Okay, so the name is bromine pentafluoride, and it has 1 lone pair. And if we go to the next slide, we can see that the lone pair is situated where you would expect the extra R group to be, or not R group, the extra atom to be. There was one, and then the angles are all the same on octahedral molecules, or octahedral electron domain geometry molecules. It's 90 degrees, and yeah, let's go ahead and go on to the last one. So this last one is, yeah, also an octahedral electron domain geometry molecule. The specific molecular geometry is square planar. The total number of electron domains, of course, is 6. And the type of, the number of lone pairs here is 2 instead of 1. And a good example of this is xenon tetrafluorine. And here you can see where the lone pairs would be. It would be on the top and the bottom of the xenon atom. And again, the angle between each atom would be about 90 degrees.